Okay, thank you very much. As usual, please interrupt me whenever you want. Also, the online people, uh, it gets to become blurry sometimes. Just let us know. And maybe I lose my voice today. Let's see. Also, let us know if that happens. So, uh, before anything else, I have to say something. Uh, we won't have for the next 2 weeks, we won't have any lecture. So next week, people are just away. The week after is Easter in Czech Republic, in our headquarters. So 2 weeks. After 2 weeks, we restart. And I should repeat it again at the end because maybe some people come. So please just remind me. Okay, so now uh, where were we? So if you remember, we define toposes, right, as some sort of categories with some structure. And then I said that I want to present 3 ways of constructing toposes. And for the first one, we needed to introduce functors and natural transformation, and we did that. And I also said that for the first one, we have to do it in 2 phases. So for the first phase, we saw some basic things like functor and transformation, as I said. And then at some point, we have to move to the second phase. And the result of the whole thing was that if you have C as some sort of small category, then the category of set to C is a topos. I claim that. Of course, I didn't prove that. I just defined it. Like the objects were just functors from this guy to set, and so if you have 2 objects, like 2 functors, then natural transformations are the morphisms. Of course, the composition of natural transformation is a natural transformation. Identity is a natural transformation. So you have a category here, right? So today I want to just do some recap on the functor natural transformation, and then we complete the natural transformation part that we started. And then we come back to this category to show that it is really a topos. And then I will say something about logic. And you remember that I said that a topos is just the stuffed version of a Heyting algebra, right? So you can ask then, what is the Heyting algebra version of this? And then I say something about logics. But at the end, we slowly go to the phase 2 of the construction. This is phase 1. And for that, I need to introduce some sort of new reading of functors, right, in this form. So then recap. So we had functors, right? So if you have 2 categories, a functor is just a map, assigning objects to objects, morphism to morphisms, respecting all the structures that you have, and you know what. And then I said that you can read this guy as a construction method going from the discourse C to the discourse D. You can read it as a variable object or an object with parameter A in C, a variable object in D. And you can also read it as some sort of realization. So read C as some sort of abstract category of nodes and edges, and then D as some concrete category like set, groups, whatever, and then you realize this abstract shape here in D. And then we also we had an extensive list of examples for functors from algebraic topology to algebraic geometry, but then we had natural transformation. So if you have 2 functors from fixed C and D, then by a natural transformation, formally, I meant just the sequence of maps from f of A to g of A for any object A in C, in this one. such that for any f in C, of course, from A to B, if you do it like this, and here like this, and of course you have f of f and g of f. So for any f, that guy must be commutative, and the interpretation simply is that if you go from A to B, at each point A, you can transform f to g, and if you go from A to B, you can smoothly transform this to that, right? So there is some sort of conceptual gap here, right? Usually it is just easy to understand categories and functors, but natural transformations are kind of complex to get. So if you find it somehow complex, just think like that you have a morphism from F to G, right? F of A to G of A, but uniformly in A, good in A, right? So therefore, it is just something that lives in D, say, but in a uniform way, right? A is an object in C, right? And okay, so also we had some examples of this. So now I want to complete the list of my examples and non-examples. So you know my favorite categories, right? So let's say that I have a post-it and another post-it here, right? So what is a functor? Order preserving map. So let's say that I have two order preserving maps. What is a natural transformation here? Let's think formally. So for any object, okay, maybe it's good to explain it like this. So I said that a natural transformation must be what? Something from f of p to g of p in Q, right? And in Q, there is just one morphism at most between any two things, right? So if there is a natural transformation, of course, this must go from f of p to g of p for any p, right? And since there is just one unique map here, simply I'm saying that I have this for any p, and I choose that unique map. This is a poset, right? If you read the poset as a category, then if something is less than the other, you say that I have just one unique morphism from that to that, right? So what I'm saying here is that, okay, let's assume that I have a natural transformation, and let's see what it means, right? So if it's a natural transformation, it must be a sequence of maps indexed by the objects here, right? Like there. And then the point is that here you have between two things at most one map. So therefore, there is just one map from f of p to g of p if it exists. Yes, these are points in Q, and then just one. So then if there is some alpha, that alpha must be just those one unique morphisms. In other words, I'm saying that there is one unique natural transformation here if and only if f of p is less than g of p for any p.
So that's the condition for a transformation to exist.
Yes, and the transformation is unique because I have just one choice. So, right? And of course, the only thing that is important is that I have a poset here. So if this guy changes to be just a category, then it's also fine, right? So you have the same thing.
So, can you just say quickly for some concrete ponderings what this is going to look like? So P is the integers and Q is the rationals.
And what are the F's and G?
Yes.
I don't know. Say you have N and the order, and the same n and the order, right? So this is just doubling, right? And this guy is tripling. They are order preserving, of course. And what I'm saying is that there is a natural transformation here simply because 2n is always less than 3n for any n. And that natural transformation is just a sequence of these unique maps.
You say there's no natural transformation.
Yes. Hmm? Of course, because it should be uniform, right? So uniformity here means just you have it everywhere. The other one that I like. So let's say that I have so two groups over one object, right? As categories. So what is a functor? Exactly. So I have two group homomorphisms, right? What's a natural transformation then? Yes, but why? Because what? Because by definition, for any object, meaning just one object, I need a map here from star to star. So therefore, alpha of that unique map should be something in H, right? A map. And also you need this commutativity, right? So this commutativity is just F star, G star, G star. So everything is just one object, right? So then you go from star to star to star to star. The point are the maps, right? So F of F is what? Is F of, so F of G. This is G of G. God, that's really confusing. No. Oh, so let's say that's because I don't need these two guys. So Mn F G, and this guy is in N. So then here I have F of any G. Here I have G of any G. Here I have what? So just the only map that I should have here. So right. So okay, if I have a natural transformation, it is simply just one element in N such that this commutes for any small g, right? Meaning that first, G of G must be the conjugation of, I have to compute, alpha star minus FG alpha star, right? You have to have this between F and G, and alpha is the conjugation, right? If it is, then it is a natural transformation, right? So let's assume that this is just an abelian group, right? Then from F to itself, because they should be equal, there is one natural transformation, or not, many. Anything is a natural transformation. And if F and G are different, there is none, right? So
When you say small, you really just mean it's on the left of
what? No. By small, I mean it is small, meaning that the set of all, the class of all objects and morphisms, all of them are small, meaning it's a set, right? So it's not like the category of sets that you have the class of objects. It is like the group.
small.
Oh, you mean it's okay? So sorry.
Oh, okay. I, it's just a, okay, never mind.
Yes. Okay. Another one. That is kind of important. So let's say that I have the category C and two objects A, B, right? In C. And then you have two functors, right? Home A and home B. I hope you remember these two guys, right? So they go from, let's say for any C, this goes from where? Up to set, right? And then it reads something and it just computes all the morphisms from that guy to C. And the main point is that if you compute it on morphism, it simply means just compose with that morphism. Okay? So you have two functors. What are the natural transformation between? There's one canonical way, obvious way, right? At least you should have an obvious family here. What is the obvious family? If I have a map from A to B, then I can compose and I get a function here, and probably that function is really natural, right? So that is one way to get at least some of them. So let's say that I have f from A to B, then you will have that, say, f star that goes from home, what, home for any C, and then it reads simply just one map, and then compose it. So G, and then after that F, right? That's just something obvious. It is natural, and I'm not sure that if I have to check, but it is natural. Let's believe me. So what else?
Sorry, just as a reminder,
Uh-huh.
home is what are A and B? A and B are yeah,
They are objects in some category. So fix the category C. You have two objects. Yes. So for any C, you get this obvious composition, and then you can construct a sequence, and that sequence is natural, right? So to check that, okay, maybe I have to do it. So to check that, you have to do this, right? You go from CA, CB, some DA, and DB, right? So here I compose with F, right? In both cases. And then what? Then let's say that I have a map from C to D. That is my G, right? Say. And then you get the home functors here. That is just composition with G. But like here, am I right? I hope I'm right. Because if you have D to B, then yes, C to D. Okay, yes. So G from the digit, right? Right. And then that is just commutative simply because if you compose with F from that side, G from this side, it is just equivalent to do it the other way around, right? So because they are on the other side. It is just the associativity, right? So it's natural. Okay. What I'm saying is this. You have two functors. If I have a map from A to B, then the composition with F is really a natural transformation here. What are the other natural transformations here? Yes. There is nothing else, right? And how do I know that? Uh-huh. Okay, fair. Then I get my F. Yes. But then how do you know that it is really everywhere is composition with F? Because you checked for A, right? And also just on identity, say. So then you have just one thing. So it should be just true everywhere. And it is. And the reason is naturality. So here's the point. So if you have a natural transformation from this guy to B, this natural transformation, okay, let's put a name here. So why not to call it YF, right? So there is always some F from A to B such that alpha is Y of F, right? Always it comes from one F. So you have to find your F first. This is the claim, right?
So what if you written that?
If you have a natural transformation, yes, Y index F, and Y index F is just the composition with F, the natural transformation that you had here. So everything comes from composition with some F. And how do I know that? Yes, how do I know that? So the proposal is that, okay, if it is, then first you have to find your F. And how to find your F? So this is just a sequence. Apply it on A. Right? Why not? Then you have the identity map here. Therefore, alpha A identity of A is simply a map from A to B. And the claim is that F here is this. Right? This is the canonical F that I have to pick. But okay, it should be that F, but I have to check this equality. Meaning that alpha and uneta and the composition with F always should be the same things. So what does it mean? It means that if I have home CA, home CB, and here I have alpha C, right? The claim is that it should be just composition with F, right? With that F. How do I know that? Naturality. So I write the obvious thing here. You have alpha A, and so let's say let's say you have G from C to A. The naturality says simply that you have composition with G. What was that? Yes. This is just a naturality of alpha, right? Again, I have one alpha. My claim is that alpha is in this form. First, I have to propose one F. This is my F. And I have to now show that the equality. To do that, I say that, okay, alpha is natural. Therefore, I have this, right, for any G. And now you can see that you know alpha C, really. Because alpha C composed with, say, you start identity here. So identity composed with G is G. You have alpha C on some G, some arbitrary G from C to A, which is this guy. So it is alpha A on identity A. This is my F. Sorry. Compose F to G. So I'm saying that alpha is always composition with F and G. Okay. Huh?
The homomorphism with the underlying of that
Mhm.
is this thing with the sets from
C opposite. So what do you mean? This? So it's a functor, right? And it is a functor from C opposite to set. And this dash is just the variable that you have to read from C opposite and then do your computation.
so that's what you're talking about here.
Yes.
So plugging in some particular C from C.
Because when I have a natural transformation between two functors, it is just a sequence for any C.
So the C's are the
Objects again in C.
and what have you shown?
I showed that any alpha is y of some f, meaning that if you compute alpha C for any C, as a function, it is just composition with some f. You read something here, you compose it with a map from A to B.
What is this? Well, you're explaining notation Y.
Yeah, that is that. So,
What is the Y?
yes, okay, y is just the first of your nada. So it's just my convention, right? For any f, you have a natural transformation. Let's call it y of f, right? So this is my kind of canonical maps here.
And so that's the way of giving you a transformation from any F. And here you want to show any transformation arises from some F.
Exactly.
And where do you have which F? So the F chosen is the image of one.
F is this. So if you have a natural transformation, you apply it on A. You have this from home AA to home AB as a function, right? Then therefore apply this function on one element, the canonical element here, identity, that is from A to A. And then you get something from A to B.
Again, the picture of the original category was category C.
Yes.
That this thing is the sets C are going to sets.
These two leave there, yes.
Now alpha A
Is a mapping set.
uh,
Alpha is a natural transformation.
alpha is not a transformation.
Yes.
What is you fix things uniform and A. Fix some.
If you plug in A, then you get a map between two sets because of this, right? So it is just a sequence of real functions indexed by C.
Where is something that depends on the structure?
Yeah, all of them kind of based on that. But the point is that, for instance, these two are functors over C opposites, right? So if you say that I have a natural transformation, simply you are saying that I have a sequence of functions indexed by objects in C opposite in some coherent way. So here you see the structure of C.
Showing that the theorem is that
Any natural transformation is just Yoneda of some f or composition with f for some f. Yoneda, yes. It's the name of some guy. Yes. Okay, so what's the moral of the whole story? It is the following. If I pretend that A, so here I have C, here I have set to C opposite. To any A, I can assign this home A, that by the way, I write like your name of A.
that's a category. No, they're on the right hand side.
This or that.
Thing.
This is just some object here, right? To any object, I assign an object. Object here is just a functor from C opposite to set. And we saw that this guy is a functor from C opposite to set, right? Right? So what I'm saying is that if I assign to any A, this guy here, and say to any morphism, I assign that unit of f. Why not? Right? Then what I have is really a copy of C inside here, right? Because you can pretend that A is this, right? B is this. I can transform any map to a natural transformation here as a map. And then we saw that any map here is actually coming from one of them. And it is unique because we constructed F based on the natural transformation. So there is a copy of C inside of set to the C opposite.
Same pattern.
Exactly. So just exactly the same, right? So that is the unit of function. So it's really a functor. So the functor goes like for any A, it is just, or another notation is this, is just home this. For any morphism, you get what you know, right? The composition. So we proved that we didn't prove that it's a functor, but it is. So you go from C to this, and then the image in C is exactly the same as C itself, right? C sits inside this bigger category. And what's the point? The point is that we will show that this guy is a topos. Therefore, it is really set theoretic. So simply I'm saying that whatever category you have, you can extend it in some sort of conservative way, because it just really sits here without any new morphism or whatever. And you can pretend that everything is just set. But set in, generalized notion of set, not just usual. Everything is a set as long as you read set in general sense. Right? And of course, you have many structures here because it is set theoretic, right? You have all co-limits, limits, blah, blah. So then you can use them. So it is kind of ideal objects that you are adding to your C. Okay, the last thing that I want to say maybe is about natural transformations. Of course, not in life. Is that it's not the case that always everything is natural. Sometimes some natural things are not natural. That's bad. So let's say we had the category set, right? And then you can expand it to the category of relations. So here objects are sets, morphisms are just relations, not functions. Not total relations, just relations. Composition of relations, identity relation, of course, it's a category, right? So it is the non-deterministic version of this. So if you read any set as the set of states of a system, then if you have a function, it's a process that deterministically transforms one state to another state. But when it's a relation, it is non-deterministic, right? So one state can go to different things. People really use this to formalize finite bit quantum mechanics. But anyway, so you have this, and then you can have just the product function. Right? So I read just a pair of two sets, and then just the Cartesian product. And if you have CD with two maps, so any map here is just two maps, right? R and S as relations. So do just the pointwise thing. You know what I mean, right? So two things are related here if the first are related and the second are related via R and S. So you have some sort of product. This is not a product in the category of relations, actually. So it's not the product in the categorical sense. The categorical sense of product is just disjunct union, which is weird. But it is some sort of. Okay, then you can use this functor to have these two functions. So for any set A, you can go from A to A times A, mapping A to pair of A. That's just a very natural map, right? So you can interpret it as like that you have a bit and you clone it. You have two copies of it. The other function that's very natural is this. You just project, right? We saw that it is just a natural transformation over set. So you read AB and you forget B, right? You kill one bit. As you suspect, these two guys are not natural over relations. If you have non-determinism, that is impossible to clone a bit, like a qubit, for instance, or eliminate it. Even worse. So that's just easy. So you play with different choice of A, and then you see it. Even worse. Not only this guy, and the same also works here. There is no natural transformation from A to this, except the empty relation. So you cannot clone in a non-trivial way, never. Not just via that function, never. That's just impossible. So this is just a baby version of the real quantum kind of phenomenon that you really work with vector space. Here you have tensor of vector spaces, and then you say that there is no natural transformation here except the constant zero, right? This is also true here, but that is more combinatorial version of it.
So you have here two categories. There's rel profitable as well.
Yes.
And you have this functor between them.
Yes, you need two functors, but I'm not telling the whole laydown, right? So let's say that what is the proposed natural transformation here, right? So you need two functors. Yes, with the same ends, right? So what is this and what is that? So here you go from the category of relations to the category of relations with identity. You do nothing. This is the functor, nothing. Do nothing. Okay. This one is this functor. So you go from relations to this. So this is just make it double and then do the product. So you have that. Oh. So what I'm saying is that there is no natural transformation here except just the constant empty, always. Okay. So next. What is next? Next is did I say hey, all the things that I want to say? Yes. So sure.
Mentioned this limiting basis for
Yes.
you first call it non-determinism. Does this have an interpretation for non-deterministic Turing machines, or is it only for quantum?
Because in both cases, okay, so the point is that if it should be really that's just big, right? You have more than even functions. So the category of relations is so big, right? You have all the functions, but not only functions, all the relations. So the point is that you have more than computable things, really. But the behavior is similar to non-determinism. So for the quantum thing, at least I know that there is some sort of axiomatization of what should be the quantum word in the category. And the category of vector spaces and that relations, both of them are instances of those categories. For non-determinism in the general sense of the word, I don't know if there is something like that. But if if I want to, so if I don't know that, then it means that I have to really encode some sort of non-determinism beyond the obvious thing that we understand here, right? So like using Turing machines or whatever. And then that's not really accurate, right? So you have.
Okay, but once I have these vector spaces, then basically I can pretend I have quantum because I have this linear algebra over.
This is the real quantum, really. But
transition function of
true. True.
but we cannot interpret the
I-
inability, like there is no non-cloning theorem for non-deterministic Turing machine.
Or maybe we can using the same ideas, but my main point is that you have to restrict your category of relations in some way to be really about Turing machines, but the same idea must go and work, right? So
If I pick a single morphism, I cannot in general tell whether it is coming from a natural transformation, right? I cannot define it in this way. So every morphism can to coherently define which morphisms are the natural ones and which ones are not. If I talk about the class of morphisms.
I see, but the thing is that one morphism cannot really see the whole thing.
Yes.
Being a natural is just about the whole category. So it's just really a local thing. So they are not that connected. So there are many cases that you can just lift one morphism, any morphism, to a natural transformation, kind of even in almost arbitrary way, but sometimes you cannot. So, Okay, so now let's say that we know everything about natural transformations. Let's come back to this category of set to C, right? My claim is that this guy is really a topos, right? So I have to check all the three axes that I have. All finite limits, the exponentiation, and the subobject classifier. Finite limits is easy, right? It is just pointwise. So first, for any finite to check the existence of all finite limits, it is just enough to check, I don't know, pullback and one, or equalizer, or product, whatever. So let's just an instance. Let's check what is one. What is the terminal here? There is a terminal. And I already said that, right? Everything is pointwise. Now it helps really to think of anything here as a variable set over C. Set that changes over C. So what is the terminal? Yes, as a variable set, just single point, right? Constant symbol, constant single set, right? So delta singleton has the constant map from set C to set. It simply doesn't care. So it reads this and returns just the singleton, and for any morphism from any A to B, it simply says yes, but simply because it cannot do anything else. You have just one element. There is one function here, right? As a variable set, nothing varies. Just one single. this notation simply means that it's a singleton, but I don't care what is it inside. So it can be just a singleton, 0, 1, whatever. Just pick your choice. The set with one element. Because everything is up to isomorphism, right? So then
So what happens if you take different objects, possibly different things, but then there's still.
there is always one unique map between any two singleton, right?
Yeah, so would that still be?
Yes.
A terminal?
Yes. And isomorphic to this. Yes. It is terminal simply because you can. Okay, I have to prove that it's a terminal thing, right? So meaning that for any f, there should be one morphism from this to this, right? If it is terminal. Morphism is a natural transformation. Of course, there is one at most, simply because it is just a sequence of some functions. Like it, alpha is just a sequence of these guys. That is just singleton. There is one map here, so there's one natural transformation if there exists one. But that obvious function here is really a natural transformation, because if you write that thing to check, here you have star, and there's just one morphism to star, always everything come here. So it's just easy. I'm not writing all the details, but what I'm saying is that there is one alpha here, and that one alpha is simply just the obvious map from any set to that singleton. What is product? You can do product also easily. Yes?
Go pick it up.
Uh-huh.
Can you label the fonts?
Yes. Why not? So if you want to check really that it is, so you have to do what? Right. So you have to go first f of a to delta, let's say, of a, and then here is delta of b, f of b, these two morphisms, and say that here I have for any map f from a to b, this is f of f, this is g of f. That is just the obvious because it is singleton. That is just the obvious singleton. This is also the obvious singleton constant map, right?
You want to show that your delta is a singleton in this category.
That is my definition. Delta is always constant singleton.
I thought you were showing.
No. I define my delta, right? I have to come up with one object here as my terminal.
That's right. You're showing it to them.
Yes. So this is by definition true that always this is a singleton and always it is identity. So to show that it is terminal, so you have to pick some f object here, meaning a functor from C to Z. And I have to show that there is unique one morphism here. And that morphism is a morphism here, meaning that it is a natural transformation. So I have to prove that from any f, there is exactly one natural transformation here. So first, uniqueness, or whatever. So my point is that what is this alpha? It's a sequence, right? For any A object in C.
Okay, I think I really want the reminder of the definition. So that makes sense.
Okay, sure. Okay, but then the final thing that I wanted to say was that, okay, so to check that it is a natural transformation, you have to check this square, and then this is just obvious simply because you have star here, you have just singleton here, and there is just one map from anything to the singleton. So every diagram with that sync commutes, right? So there's nothing to check really. So if you move me here, So, what about product? So you have FG, say two objects here, and you want product. So you mean you need one functor H, two natural transformations as the projections, right? So what is my H? H must go from C to Z. What is H as a functor? But it should be obvious, right? Exactly. What else? So always I'm saying that it is pointwise, so it means this. What is H of some F going from A to B? What else, right? So do F here, G, F of F, G of F. So that's a functor, of course, you have to check, but it is. And then you need two natural transformations, say P0, P1. So what is P0 then? So P0 of A must be a map from H of A to F of A. That's of course projection. You have the same for P1. You have to show that these guys are natural. And then you have to show that this guy is really the best cone. But everything is just pointwise, right? So you do it for any A, you get your maps or commutativity or whatever, and then you see that it is just natural, right? So that's easy. And the same for other limits. So point, you have all the limits here in this category. And even better, all the limits are computed pointwise. The same also true for co-limit. All the co-limit exists here, and all of them are pointwise like this. But we don't need it for the axiomatization of the topos, right? Yes. Yeah, like this. So if you want to define it, so you define it for any A as the co-limit of the applications on A, and then everything just uniquely determined there, right? So now we have to do the harder part, the exponentiation. That's just a nightmare. So you remember that one specific case that we had here. So we talked a bit about the exponentiation. So now we have the full scale beast, right? So I have F and G in this category, and I need some H as the exponentiation and some map, but I don't remember how I write. Yes, this as my evaluation, right? Such that it is the best, blah, blah. So, okay, let's first define H. Any idea from someone who is not really familiar with it? Just come on, that's
Then something like point-wise, or with some hedging, some with something like
no, okay.
just taking some parts of the category and taking the natural transformation.
That is also good. Yes, that's good.
Holes that something of that, but I don't know.
That makes sense. Okay, so first let me just write it down, and then I will explain because you know. So what is H? H is a function. Okay. What is H of A then? Huh? It is the following. The set, it should be a set, right? Of all natural transformations, let's say NT, from home A, nothing, times F to G. That is really annoying, isn't it? But there's some sort of mismatch of the levels in the intuition, right? So why natural transformations here? So it should be just some real set, but what? Yes, sorry. And then there is one obvious map, right? So it is composition here. Sure.
Maybe it's clear, but how do we know it's a set?
Yes, you don't know, obviously. It is not easy, but let's say that we know for some reasons that it is a set. Yes, it can be big, but it is not. That's a real concern. But
So you're saying
it is a set as long as C is a set. But I won't explain it. Right? Sure.
So if more small,
The small category means the C is a set. No. I mean C is a small. So C, the size is a set size.
so see it's
Yes, it is small or any small. Okay. And H is a functor. I want to say that if you have a map from A to B, then you know how to do it here by composition, let's say. And then, wow, what is this evaluation then? It should be what? It should be a natural transformation. So I have to define evaluation on any B, say, or any A or B from HA times FA and times simply because product is pointwise to G of A. So here I have one element in F of A. Here I have a natural transformation like this. So you have alpha and X. Your alpha is a natural transformation from home of A nothing times F to G. Your X is an element in F of A, and at least there is a canonical way to really apply one to the other, right? So you compute alpha A, right? It would be from home AA times FA to GA, right? Pick identity here, pick X here, you get something in G of A. Wow. Very natural, right? Okay. Lesson 1. Yes.
I understood. But this home times F is not a mapping from not
It is because
C to self.
dash is here, right? So home is from C opposite times C to set. Yes. Yeah, F is fixed, G is fixed, right? For two functors, I want to come up with the H. So F and G is fixed. So now you have to define your H and A. And I'm saying that A, pick the home, it is really a functor from C to set. This is also a functor from C to set. The product means the product here in C to the set. So you have a functor here. You also have a functor there. So natural transformations here. Yeah. Ah, that's weird. So lesson 1. You never think about this object like in the natural world. So if you are doing your mathematics, you don't say, okay, let's consider this weird guy. But now you have to simply because it is exponential. Because you know the behavior of this guy inside here. This is the exponentiation. But the set theoretic description is a mess. And who cares? So the only thing is that I have to show that it exists. Sometimes maybe I have to compute, but the second thing is that now I have to explain what does it mean really? Because that's just weird, right? The explanation is not that hard really. So the thing is this. So let's say that I have something like this. This is my C, some sort of tree, poset, whatever, right? And F and G are C variable sets, right? I'm using my intuition. So some sets that vary over this, right? So meaning that at any point I have a set, and then when I go here from here to there, then it changes, right? Okay, I have a variable set, two variable sets, F and G. And then what is H is the exponentiation. So it means somehow intuitively all the maps from F to G, right? All the variable maps. So then you say that what is HA? So what is all the variable maps here? So now I want to use the logical intuition that we have. So let's say for a moment that this F and G variable sets are some propositions, right? And F is a proposition, G is a proposition. By F of A, I mean all proofs of F at A, right? At some point, I have some proofs of some proposition. Sometimes it is empty, sometimes it is big, so whatever, right? So you have two propositions and then, right? So then what is HA? It is all the functions from F to G at that point, meaning all the proofs of the implication, right? So you want to prove at this point, right? You want to go from F to G. What is the proof if you have two propositions, right? What is the proof at this point?
So you certainly writing F and arrow G, not F with A, arrow G.
Yes. Because the point is that you don't do everything just pointwise, right? For the exponentiation. The idea is that H captures all the maps from F to G. H of A should be intuitively all the maps from F to G at A, but it does not mean that it is FA to GA. We don't know it, right? So now I want to try to understand what it should be, really. What I'm saying is that it is a proof from F to G, right? So if you have a proof now of G from F, the first important thing is that it will be a proof later. Because if I prove something, then later maybe you prove that the Riemann hypothesis is true or it's not. You have some fork in the future, but I don't care, right? Always my proof is a proof. It works there, it works there. So it's not really a function from A, F of A to G of A. It is a function from F of B to G of B for any B above A. Right? Intuitively. Yeah? At least you need this state.
Is this a concrete example?
Of course not. Because, okay, the least possible concrete thing was set to the two. And last time or the time before we saw what happened. So that's just a mess. It doesn't help.
So what's wrong with it?
What's wrong with what?
Why can't you give a concrete example?
I can, but it doesn't help your intuition really.
Can you say your example again? So you've got this category.
Yes.
Parameterize.
Yes. As some, let's say that it is this poset, see? Okay.
But we shouldn't think of it as actually parameterized.
Yes. So meaning that just think intuitively, right? You have a proposition, you have some proofs of it now, some proofs tomorrow, and then maybe your set expands, right? Maybe, yes, maybe you find a proof, right? So then F and G are, and not really. Okay, let's not do that.
All right.
Let's just keep in mind that this is just time. When time passes, you find new proofs, and sometimes something is just empty, and you find a new, just one proof, whatever, right? So my point is that then all the maps from F to G is kind of all the maps that transform one proof to the other proof, one proof of F to the other proof of G, right? It seems that's reasonable, right? So then, therefore, for the exponentiation, I have to come up with some explanation and of that what are really the proofs of the implication, right? You have two propositions, but is a proof of the implication. My point is that if you have a proof of implication, at some point, it persists, right, to the future. Or if you want to just really think of functions, if you have function from F to G at this point, so maybe your F changes, but you have some incomplete data, and for that incomplete data, you know how to transform F to G now. And it keeps working when you go to the future, right? So if I want to formalize then this notion of proof, whatever it is, at least it should be something for any B, not just a function from f of A to G of A, from any f of B to G of B. It should be some sort of sequence of all of them that says that here you have this proof, later also you have a proof, it is a version of this, etc. This is first thing. The second thing, which makes everything harder, is that actually it matters how you go from A to B, right? Because different ways changes the proof in different ways, right? So then actually you don't have this, you have this. You say this is the way from A to B, then I have a function from f of B to G. Right? This means that I know all the functions above, parameterized say by B and then with F, right? And of course, I don't want it to be arbitrary, it should be natural. So if I say that it is natural, then it would be like this, right? But then it means something really. If I have a natural transformation, simply I have a way to say that when you go up, how to transform f of B to G of B in a coherent, uniform way. So I'm not, it is just the usual intuitionistic implication, right? With maps, with all the things, right? Okay. You can prove that it is really the exponentiation. I won't do that, of course. The last thing is just that sub-object class. I have a similar problem somehow with this. So let's say it should be, of course, because it is an object, instead to the C opposite, it should be a functor, right? Somehow encoding all the truth values for those variable things, right? Okay. So what it should be, let's come back to this example that I have. So what is all the truth values at A? Because I have to define now again omega. Or maybe I have to define it first like that, and then I should explain. Okay, first, what is omega? You have no idea. So it is the set of all co-sieves over A. What is a co-sieve? It is a cat. Okay, what's a co-sieve? That's right. Yes. Co-sieve on A or over A. So you have a category like this. This is your category C. This is your A. So it is just a set of morphisms in. Okay, no. it's cohesive. So it is the set of morphisms from A to something like such that it is closed under composition from above. So if you have this, then if I compose it with any map, it is also inside the set, right? So it is a set S of maps like this, maps says S of maps from A such that if F from A to B is in S, and you have a map, say, B to C for any G in C, then the composition, which is simply FG, yes, GF. GF is also in this, right? This weird thing is simply just an ideal. So if your C is just a poset, and I don't care about the morphism, I just pick not the morphisms, but the end of the morphisms, right? Because there's just one morphism from anything to anything. So it is just some upset. It's a set of points that's closed under doing the opposite, right? If you go up, you have to pick that as well. Huh? And if it is just a monoid, it is an ideal. It's closed under composition, simply.
Yeah, picture about the figure, so we see set of those points or of those maps.
Set of maps, yes. So one cohesive is a set of some maps from A to somewhere else, such that it is closed up. Right? I guess yes. Yeah, one is left, one is right. Right? It is just a common generalization of an ideal, left ideal, and offset in posets, right? You see the offset thing, right? Okay, so first on objects, all the cohesives over A, and what should be omega of some F, say F from A to B. What else, right? So it is omega A to omega B, it should be, and I have to define it, so let me define it then. It's a function. So omega F is a function that reads S as some cohesive over A, and it must return the cohesive over B. What is the cohesive? So you have A, this, you have a collection like this is S, and you know how to go, is it I'm missing something, huh? No. Yes, that's right. So then you have a map. A map is from A to why do I feel something is wrong? What is omega of F? So I have F from A to B. I have cursive over A. Then I have a map from A to B, F, and I have to come up, come up with a cursive here. Right? So what should be the cursive? All the maps such that if you compose with F, they are inside S. Huh? F is this way. So you have to define this guy, right? This is omega F of S. So I'm saying that this is just all the G, B to X such that if you compose G with F, it is in S. Huh? So it's a function, and somehow it encodes all the truth values in that category, and that's kind of weird. So I want to explain now why. Let's say yes. Yeah, also I have to say that. That's right. So you need also one map from 1 to omega as your true. And I forgot to say that, right? So 1 in this category simply is just singleton everywhere. So therefore I have to just, and it should be a natural transformation, meaning that I have to pick TA in omega A for any A such that it is natural, right, in A. So what is just the obvious element in omega A, all the cosieves over A, just a full cosieve, everything over A. Yes? So TA is just a set of all maps from A. All of them, everything. Yeah? You have to show that it is natural, you have to show everything, right? But anyway, so the intuition is this. So this weird cosieve thing really captures the truth value. So how to explain that? Again, let's work with the variable sets. Right, so you have variable sets. This is my C. And then this, remember what is the role of this omega? It is just classifying being a sub-object, right? It's a sub-object classifier, meaning that for any F, any G, which is monic, you need a unique map here such that this becomes a pullback, right? Simply, this is just a characteristic function of being a subset. It reads something here. It would be 1 if and only if it is in G, and otherwise it can be something else, right? So here, you have, say, GF as a variable set. You have to show that being monic is pointwise, meaning that any G of A is a subset of F of A somehow. So you have a variable set and variable subsets of it, right? And then what is the different ways that G of A sits inside F of A for different A's? This omega does that, right? So if you are, so what is omega of A? This is A. Omega of A, here, omega of A is all possible things that can happen for some element of G to be, some element of F to be in G or not to be in G or whatever, right? So different possibilities are what? If you forget about the morphisms, simply it would be an offset, right? Because you pick one element, the element is not in G, right? From here above, right? So let's say that here, you pick an element in F of A, it is not in G of A, you go up, 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 up. At some point, maybe it becomes an element of G of A, and then it remains there, right? So any subset which is offset captures that some sort of truth value that that guy now from this time it is inside your set, right? It is just 0, 1, right? The usual truth value is 0, 1, but 0, 1 over the nodes such that if you get 1, then it will be 1, right? Again, the problem is that you have different morphisms, right? This is not the case that you get 0 or 1 for B, that here that guy goes to G of B. The point is that for different Fs, different things can happen. For some F, You may transform your element here inside G. For some, you may not. So then what you have to have really is a set of morphisms from A. These are the morphisms that force some given element to go inside G, and it is closed upward. Because if you go inside G, you remain inside G, right? Therefore, you need a cosieve to capture that. So another way to say that is this, that you, for any map, you assign 0, 1, of course, right? Natural in B. Any cosieve is something like this, right? So you don't say that for A, it is inside or not. This is just 1, 0, 1. Like the exponentiation, you have to do it for any B upside, right? And not just for B's, for different ways to transform A to B. Okay. Also, you have to check that it is and what is this? This means that it is already inside G. It is true. It is inside G. It is always 1. It is constant 1 here. This one, right? So, okay. So that's it. And the last 5 minutes, maybe I have to say something philosophical. So that proves that this guy is a topos, and maybe it does not say anything to you.
Set theory, do you need to show this?
Oh, way later. So you need, of course, some sort. You need everything in ZF, C, except let's say these guys. You don't need really replacement. You don't need foundation. You don't need infinity because I don't use any infinity here. And I guess for separation, you need just delta 0 separation if everything is bounded. So I don't do anything unbounded.
You're saying you do need choice.
No, also no choice. Yeah, of course, yes, power set you need. But of course, right? So for some arguments you need, for some, but for the things that I'm doing, everything is canonical. So I'm not doing any kind of choice really. So how much set theory I need to run these things? Because everything is based on sets, right? So yeah, this set to the C is the topos, for instance, right? To prove. Yes. So okay, the last thing for today is this. That so we saw that this guy is a topos. And this is just the first phase of the first way of constructing things. That's not the good one. You have to do other things to get the full scale power of this. 1, 2. I said that any topos is some sort of, you remember this thing, right? So that you have Heuting algebras and you have toposes. So here you have algebras, you have just one morphism at most. You care about probability, you here care about different morphisms, proofs, and then this guy is just the stuffed version. It lives above, kind of, in some weird sense, I mean, above Heuting algebras, right? And then I said that you have topological spaces as topological spaces. So let's say this, and opens of it is a Heuting algebra, right? And then you have intuitionistic logic. And it is another example of Heuting algebra, and it shows why these guys are related. Somehow you have to generalize topology to get this, and generalize logic, which is just type theory, right? You have also not just truths and probability formulas, also morphisms like proofs. Okay, now I have a topos here. What is the Heuting algebra version of this? Of this topos? right? It is the stuffed version, more morphism of some algebra, right? The algebra is this, when you forget about your morphism. So first, my C should be just a poset, because I don't like morphisms, at most one morphism, right? Because just probability. I don't like set, but this guy, 0 less than 1, just the obvious poset 2. This is just a poset version of set. If you forget about all the elements, then either the guy is empty or not empty. There are two things, right? So then the Heyting algebra is the propositional version of this, which is just that. All what? All order preserving maps here. What is an order preserving map over a poset to 0, 1? You are assigning 0, 1 to the elements such that if you assign 1, then it is 1 everywhere, right? So this is simply just the opposites of P, right? The set of all opposites. Any map here is opposite. And the order here, as we saw before, the natural transformation order is just the pointwise order for any F and G. So here it would be just this, the inclusions, right? So this is what a logician calls what? A Kripke model. You have a poset and then subsets, and you read that those subsets as propositions that become true and remain true over time. A topologist works with this and calls it Alexandrov space. It is a space such that the arbitrary intersection of any family of opens is open. So then I'm generalizing simply the Alexandrov spaces to the case that I care about morphisms, or if you like, Kripke model to the setting that I care really, not just about truths, but also what proofs, right? That's the game. But now, the last thing is this. There are more topologies than this. Not any topological space is Alexandrov, right? Therefore, it means that this is not the full generalization, right? It is just half generalization. You need the phase 2 to go for the full topological spaces, right? To lift them. And I will explain it in 2 weeks. Okay, then I should, I guess, stop here, or because I don't have it. Okay, I should stop here. Sorry, but any questions?
During these notes you have on your website or anywhere, where if you want to read more details about readers.
Some of them, yes, it is in that semi-book. Mostly the categorical parts. Okay, so except the definition of it, the topos and the construction of these toposes, everything else is there, really, because it is mostly category theory. But real topos theory of the things that we are starting to now cover, they are not really there. So, but they are not in the draft of the book, but of my book, but of course it is in the references that I provided there. So the best of them is just MacLean-Murdoch sheaves in geometry and logic. So. Sure. Ah, yes. Okay, I said that, but I can say it again. So next week and the week after, we won't have anything. Okay, so.
But the next week, just to.
I know, but this is the excuse to get some rest.